Hi there, I'm Andrei Korenkov, a PhD student at Stanford University focused on AI and robotics. And in this video talk, recorded from my home due to COVID, I will try and convey to you what I think is a pretty important question for my field, which is, what is AI? Now, presumably you know that AI stands for artificial intelligence. This is a pretty well-known idea. But I would bet if we were to discuss what the term artificial intelligence actually refers to, we might have pretty different opinions. See, I think as a PhD student, as a researcher focused on AI, my idea of what artificial intelligence refers to would not be the same as yours. And so that's what I want to convey in this video, what I as a researcher in AI view the meaning of a term to be. And also, in addition to that, why not also share what do I do as an AI researcher? What is AI research? How does AI get created? What is a PhD all about? I want to try and get across all of those things that I think are kind of related to this. So, to get those two things across, we're gonna discuss 3 different topics in turn. First, we're gonna go ahead and tackle directly what is AI. We're gonna dive deep into that topic, really break down the definition and meaning from my perspective. Then we're gonna take a break from AI and quickly discuss what is research, what is academia, what are PhD students actually doing with their time, and why does it take 5 to 6 years to be finished, at least for many of us. And lastly, we're gonna talk about the combination. We know what AI is, we know what research is. What is AI research? How does it work? I'm going to go into some specific examples and really try and give you an idea of what I do, how AI research happens. So let's go. Let's start with the first of these, which is, what is AI? And so, as I've said, I think you know it's artificial intelligence. But if I were to ask you what is the definition of artificial intelligence, I think many of you would say it has to do with programs that exhibit human-like intelligence. It has to do with, things, maybe like Skynet in the most extreme example, but also like HAL, like R2-D2, examples of robots and machines that act with human-like intelligence. And that's fair. These are examples and these are relevant to artificial intelligence. But I have a pretty specific definition I want to get across that really relates to what we have today with AI. And it turns out, to get a good definition I agree with, you can actually just go ahead and ask Google for its definition. And it's pretty good. So you can take a look here. The definition that you find from whatever dictionary we use is that artificial intelligence is the theory and development of computer systems able to perform tasks that normally require human intelligence, such as visual perception, speech recognition, decision-making, translation between languages, and things like that. So, I like this definition quite a bit because it focuses on the real journey aspect of artificial intelligence. It is the theory and development. It is the effort to create something and not the end product. It isn't a computer, it isn't a system, it is people's efforts to create a theory and develop the systems that solve various tasks. It's sort of like electrical engineering or civic engineering or computer science. It is a field devoted to a set of problems and the people working in that field, and there are byproducts of artificial intelligence, which are the programs and systems themselves, but they aren't, AI itself, or at least I would say so. Now, with that definition established, you might be asking yourself, what's the rest of this talk going to be? I mean, you just gave away the answer to the question, and that's a fair point. And the reason that I did that is I really want to dig deeper into the meaning. I want to really discuss the terms involved. I want to get into the specifics and some of the nuances and try and explain some of the ways in which I understand AI in specific ways that might differ from people who do not work in AI. But first, we're gonna take a little break to discuss the origins of AI, the origins of the term artificial intelligence, and not necessarily AI itself. And the term comes from a proposal for a 1956 workshop from John McCarthy, which we can actually still find on Google and read today. So as you can see, it says we propose that a 2-month, 10-man study of artificial intelligence be carried out during the summer of 1956 at Dartmouth College. And the study is to proceed on the basis of a conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. An attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. We think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists work on it together for a summer. Right? An ambitious proposal in 1955, and really what kicked off the notion or the term artificial intelligence, which has since been adopted and pretty much is the standard nomenclature. But of course, with its usage, what it means today and the specifics have changed. And so let's dive deeper into the nuances of the definition and the meaning of the term AI. Starting with computer systems. So in the definition, we know that it is the theory and development of computer systems. So let's start very basic, very simple review. What are computer systems, or what are computers? And I know you have a computer. I know that you are capable of using one. So this is really just review and emphasizing. And again, we can just ask Google for a definition to really know what the term means. And here again, I think it's quite good. It's saying that a computer is an electronic device for storing and processing data, typically in binary form, according to instructions given to it in a variable program. So, pretty straightforward definition, but good to have nonetheless. In a nutshell, computers are machines that take instructions to manipulate data. And next, we can talk about what can we make computers do, and obviously we can do a lot. So right now you're probably using it to watch this video, and we can do a whole lot using programs. So here's an example of a program, some simple code that, when run, produces this image. And so the way you're watching this video right now is via a program, via a set of instructions, kind of like that tells the computer exactly what to do. And today, for the most part, AI, computer systems, right, the theory and development of computer systems, is like that. The computer system is usually a program or something, some set of instructions carried out by a computer. So you should really kind of think of what is being done with AI today, what is enabled by AI, as being programs, as being fundamentally no different than your browser or the apps on your phone. These are sets of instructions that have inputs and outputs and process data on a computer. In the far future, probably AI will be much more different from your browser or from apps. And I mean, of course, the way these programs are implemented are quite different. But nevertheless, AI is still fundamentally programs on computers today. So, next, we can tackle the big one. So we know that we can develop computer systems. And next, we want to talk about what capable of doing tasks that require human intelligence means. And for that, we need to talk about the big question, what is intelligence? And again, we can maybe just ask Google for its definition and see if it's good and suffices. And what we get is something like this: the ability to acquire and apply knowledge and skills, which is pretty good, but also a bit vague. What is the ability to acquire and apply? What do these mean specifically? So maybe we can look a bit more. And instead of just asking Google, also ask Wikipedia. And if we do that, we will find that in fact, there is a whole paper full of definitions. this paper, A Collection of Definitions of Intelligence, released in 2007, that has dozens upon dozens of definitions of intelligence. And out of these dozens of definitions, the authors come up with a combined definition, which is a measure of an agent's ability to achieve goals in a wide range of environments. And I think this is a good definition that really captures in a wide sense what intelligence is. Being able to do things in various circumstances and overcome different challenges. Now, we can take an example of what intelligence might look like. A very simple example actually, which is why the definition that is so general can be useful. So here you have an image that's showing a little agent, a little dot, making its way from point A to point B and not hitting any of these blue dots along the way. And that is a search problem, finding a way from A to B. And that seems very simple, right? I mean, of course, on a 2D grid, you can find how to navigate from A to B and not hit some obstacles along the way. But in fact, if we zoom in and look here, this algorithm, A star, was developed for this robot, Shaky, in the 70s. And this was part of AI, developing a search algorithm. And that enabled this robot to move around. So we can have very simple examples of intelligence and things that qualify as AI, actually. Now, we want to make a small distinction, which is not all things that look like intelligence are necessarily AI. Rather, AI deals with what humans are good at, right? In the definition, we said that AI is a theory and development of computer systems that are capable of doing tasks that require human intelligence, not just intelligence. And that's because here in this image, we can see there are algorithms, there are computer programs that solve different challenges in different circumstances, in this case, sorting. So putting a bunch of numbers in order from lowest to highest, that is a task that computers are very good at. There are many algorithms to do this. But it's not AI, right? Because even though you might have different types of numbers to sort, and even though it is accomplishing a task in different circumstances, humans don't really do sorting that easily. It's not something we're really good at, whereas for computers, it's fairly straightforward. So this is an example of a computer science algorithm, or a family of computer science algorithms that aren't AI. Now let's look at something that is an example of human intelligence. Here, for instance, recognizing what is in this image. Okay, we can all look at it on the left and see that this is a cat. But for computers, because what a computer receives this image as is just a bunch of numbers, this task is actually very non-trivial. It's very hard to write just a set of instructions that the computer can follow to tell you this is a cat or a dog or whatever. So this is an example of a task that requires human intelligence, and therefore a task where we would try and tackle it with AI to develop some computer program capable of doing this task of recognizing what is in this image. So let's review. What is AI? AI is the theory and development, so the overall effort to create something, of computer systems. So that's usually computer programs or algorithms, but sometimes also, of course, there's hardware involved, like robots. But broadly, things involving computers that can perform tasks, so that can do things, which require human-like intelligence, where intelligence is achieving particular goals in a variety of conditions. That's a very general, but also somewhat nuanced definition of AI. Right? It's not a robot, it's not something like HAL, where it's a single entity, it's more of an effort, a collective effort by many people. Now, that is AI, and now we can dig into more of what AI is in practice in our world. And to start with, we can talk about what types of things do we use AI for? What are these tasks that we try and make computers do today? And this is actually very true of AI research, that we actually tackle very specific individual tasks. And these tasks are organized by subfields. So there's a whole kind of set of categories of planning and logic, optimization, etc. And we can actually look at a taxonomy here of various things that we try and tackle with AI. So there's things related to images with computer vision, there are things related to language with natural language processing, there's of course robotics, more of my field, and so on. So it really is true of artificial intelligence, the field of research and development, that we usually as researchers specialize in a particular type of task and category. So there's all these tasks, and that actually brings us to a very important point with respect to what is AI, which is general versus narrow AI. And here's a nice little infographic from Analytics India Mag to show the difference. So narrow AI is pretty much what we have today for the most part. These are algorithms that can do one task really well, so like play Go or maybe drive a car, but they can't do anything else. So your Google Translate can't, answer any questions about the latest movies or anything like that. And Google Translate cannot drive a car. And this is true of all AI systems and programs today. They can do one thing really well and nothing else. General AI is more what we see in fiction and conceive of as being kind of the end product of AI. It is more human-like kind of machines like HAL that can speak on many topics and do many tasks and do all sorts of things like humans can. But right now, we have is narrow AI. We have things that can do individual tasks. Now, how do we do these tasks? Well, we use different AI algorithms, and these are also categorized in different types. So we can look here in this little taxonomy. There's various families of algorithms. So there's symbolic, sum-symbolic, machine learning. We can look here, and again, there's different types of planning and machine learning. And even within just one type of machine learning, which is a very popular family of algorithms today and deals with learning from data and enables a lot of great things, there's many, many different algorithms. So that's kind of an important thing to know is, in general, there's never one AI, there's no Google AI, there's no Facebook AI, there's a bunch of different algorithms that can be applied to a bunch of different tasks. And now we can get to our last point with respect to what is AI, which is a very quick history of AI and what it's gone through. So here is a nice graphic from VTB Capital showing that we are now in the 7th decade of AI. Broadly, we started working in the 1950s. And what's interesting is many different kind of techniques and waves have gone through AI. So in the 60s, there was a lot of excitement and hype and belief that we can solve everything, and a lot of attempts at really not using data, at not using learning, and instead using hand-coded algorithms. And then in the 70s, this really didn't work so well. So there was kind of a crash, there was a winter, an AI winter, that lasted until the 80s. Then in the 80s, there was a bunch of excitement again. And now we are in the 2000s, and we are in another renaissance. So over the last decade, a bunch of new algorithms and techniques, mostly related to machine learning or leveraging data, have come out that have enabled us to make a lot of progress on some very important and difficult AI tasks. And so AI is really being incorporated into a lot of things due to these improvements. Okay, so that's AI. I hope that kind of made sense and wasn't overly boring and me getting into all these nuances. And next we can get into what is research, so that we can then go into what is AI research and what do I do and what does AI research look like. Okay, so this is going to be pretty quick because you probably know what research is. Research is a detailed study of something in order to discover new information or reach new understanding. It's trying to figure out something new with respect to a particular topic. And in practice, it looks like this, or at least in my case, and in computer science, usually it looks like this. It's a desk job. You go to your office, you work on your computer, you send messages, you send emails, and etc. You work to try and get some new results on something, which we can discuss next. Okay, but how do you try to reach this new understanding? What do you actually do with a computer? Well, we can quote from Wikipedia and say that in academic publishing, a paper is an academic work that is usually published in a journal or conference and contains research results or reviews existing results. So once you actually get some results by doing experiments on your computer, by various means, you actually write them up and share them with your community in a paper. And of course, also quoting, a paper may undergo a series of reviews, revisions, and resubmissions before finally being accepted or rejected. So there is this component of a community, of sharing your results with other researchers in your field, and of having these researchers actually review your work and tell you, yes, this is good enough, there's no problems, it can be shared, or no, you should revise this, you should change it, you should correct this before it can work. And let's look at an example of a paper, and one you probably know the effect of is this one, The Anatomy of a Large-Scale Hypertextual Web Search Engine, written by Sergey Brin and Lawrence Page when they were PhDs at Stanford. So this is the paper that kind of outlined how Google worked or how it got started. And this is pretty much what papers look like. They have a title, you know the authors, there's a summary or an abstract at the top, and there's some sections like introduction where you talk all about why your problem is interesting and what you've done, generally speaking. Now, as mentioned, you can present papers at conferences, which is pretty common in AI. And again, quoting, an academic conference or scientific conference is an event for researchers to present or discuss their work, together with academic or scientific journals, where journals are just magazines that have papers in them. Conferences provide an important channel for exchange information between researchers. And that's what this looks like, or it used to look like before shelter in place. A bunch of researchers ended up in one place and all talked about their research with each other and gave talks and presentations and shared their work and let others know that it exists and it's worth reading. And also just, chatted over coffee and made acquaintances of other people working on the same types of problems. Now, besides papers, there's another thing that people use to convey their new findings or papers, which is posters. And research posters summarize information or research concisely and attractively to help publicize and generate discussion. So they look something like this. You have a title, you have authors, and you have less text than you would have in a paper. A paper is like 6, 8, 10 more pages. I mean, there's a lot to talk about. And of course, you have graphs and pictures and so on. So again, this is quite common once you get some results to share it in a poster. Okay, so that's kind of how you share results. Now, how do you get to the results? And we can sort of summarize the process at a high level like this. So in general, you have an idea, you think of something that might yield new information or findings, you think about it, and you ask yourself, is this actually interesting? Might it actually work? If it seems like it might, then you pitch the idea to collaborators. You need some other people to collaborate with you, typically at least a professor to guide you on your way, unless you are yourself a professor. And then if people agree that this seems like a good idea to work on, you work on it. You implement experiments, you come up with hypotheses, you come up with techniques to do the research, etc. We'll get into how that's done a little bit more later. But in general, you try out a lot of things. So you work on it some more, you work yet more, you have many things that don't work, that are dead ends, until finally, hopefully, you get something that yields results and gets you new information and gets you somewhere. And when you get there, what you do is you write and submit a paper. That's when you can say, look, I found something interesting, you should check it out, here are the results. And then if you indeed found something good and the paper is accepted to a journal or a conference, then you usually present it at meetings or talks, etc., maybe at a conference, and you got a paper, and others read it, hopefully, and others build on top of it, while you yourself go on to have new ideas, and the cycle continues. So we can actually, here's a nice graphic kind of showing that there is this upper cycle of having ideas, getting collaborators, and then doing the research, which is its own cycle of trying a bunch of things over and over until finally something works. Then you can publish, and then you can go back to the idea stage again. So that's research. And let's cap things off with what is AI research? What do I do? What do people in my field do? How do we get new AI results and algorithms? And we already said what is AI and what is research, so I guess you kind of think, yes, I know it's research on AI, and you're right. So I'm going to go into some of the specifics and some of the things that aren't obvious from what we've already said. So what do AI researchers do in particular, as opposed to, let's say, any other researcher? And I think this is kind of how time is spent. Most of it is on thinking about ideas and then actually getting them to work, or getting them to the point where you have results that are interesting and have a new algorithm. This is maybe 75% of the time is just agonizing over how to do things and then trying to do them. And then the rest is, it does take a while to write papers, to make posters, to go to conferences. That's also a good deal of what we do. And in fact, in AI, conferences are the main things you present papers. And this is actually a website that exists listing different AI conferences. And you see they're grouped by different categories. So there's robotics, computer vision, natural language processing, as you've said. We have these different kinds of tasks. And so you have usually 3 or 4 major deadlines for your type of research that you can try to hit and get your paper accepted. And that's usually, in most cases, what people do. So we usually try to go to conferences and present our papers. And now let's move on to an actual example of a paper and talk about the process of getting it to exist. And in this case, the task that we tackled was task-oriented grasping. So usually what is done in robotics, or what has been kind of more approached, is the problem on the left of just picking up an object. And what this paper was focused on is more a problem of task-oriented grasping. So if you know you want to hammer something or to sweep a bunch of objects, how do you pick up an object then? And actually this is a lot trickier, because you need to not just think about how to hold an object in a stable way, but also how to then use it to accomplish something. So that's at a high level what we did, and here's roughly how that went. So in April to August of 2017, this was a while ago, this was when I was just starting out in research at Stanford, some of the team members, and I'm listing everyone involved here, basically did a lot of discussion, right? So there were months of just talking about it. Then after that, me and another master student got drafted in to work on a project and kind of help out with some of the implementation. At that point, more of the senior people took care of leading a project. Then for the next several months, there was more discussion, and then at the same time, we were trying to go ahead and implement some of the necessary things to accomplish the project. So we were implementing, the simulation framework to do this. We were implementing some of the neural net models, etc. And then finally, in January of 2018, we had the deadline. And then there was a lot of work to get this thing done. Just in the last few weeks, we had a huge number of output in terms of getting the algorithm to work, showing it works in simulation, and showing we can actually run it on the real robot. And then we were writing and writing and writing the whole week and putting in results until the deadline. And the deadline is pretty specific. You can't just submit your paper a day late. So we were working frantically and submitted it 5 minutes before. And that's not atypical, at least in my case. Often you work very hard in the last few weeks to get a paper finished up in time for a deadline. And here's what it looked like. Here's what a paper looks like. Pretty much we have the title, we have the authors, we have the abstract, introduction, a little figure there to get across what the paper is about. And we also made a poster to present at a conference. And here's what it looks like. As you can see, we try to have much less text, a lot more images, and really make it easy for a person stopping by, walking around, looking at different posters, to talk to us as the authors and get an idea of what this is about and why it works. And here actually, we also made a video. You can see there's kind of a talk on it as well. Now, we presented this work at RSS, and this was my first big conference. So I was, of course, pretty excited to go and see what it's all about. And in fact, I even made a little YouTube video back then to get across the experience. And I'll probably just go in and splice in a few minutes of footage of that here, so you can also get an idea of how going to the conference was like, and yeah, see what it's like. So I'll be back talking to you in a few minutes after you see this video of what the conference was like.
Robotics, Science and Systems, June 26th to the 30th, 2018. The Robotics, Science and Systems Conference has a long history of bringing together researchers in all areas of robotics from around the world for an engaging and focused week of single-track presentations, workshops, poster sessions, tutorials, and fun. This year, once again, we solicit your best work. So says the conference website, at least. I attended this event and made this video to convey the vibe of it, as well as some of the substance. It is a single-track conference, meaning that there were a bunch of talks in one big room, and everyone attending saw the same set of talks. Most of the talks were these short 5-minute talks summarizing the papers accepted. The slides were recorded as videos, and so the speakers had to be very well practiced to not mess up. There were also 4 keynote talks from noted researchers such as Catherine Kuchenbecker, and 3 early career spotlights for up-and-coming researchers with impressive work. In between all these talks, there was the usual mingling with free food and coffee, all in this incredible-looking Carnegie Music Hall. RSS is a top-regarded conference in robotics alongside ICRA and IRAS, and was started in 2004 as a bit of a splinter group to, quote, be a smaller conference, a little bit pushing reviewing standards in robotics and trying to highlight kind of the coolest robotics research in every year. It is not so small anymore at 1,000 people, but still considerably smaller than the likes of NIPS or CVPR. The conference also has less industry presence than other top AI conferences like NIPS and CVPR, with companies being sponsors but not taking up much space. And its single-track format ensures a very focused presentation of a small body of work representing a cross-section of all of robotics. Walking around the poster session, you see papers on planning, on learning, on optimization, on systems research, and on just about any problem within the field of robotics. You can see the poster for post-CNN just there. This year there was a bit more presence for learning-based approaches. For example, learning task-oriented grasping for tool manipulation, which you see me presenting alongside Quan Fang right there, and many works on reinforcement learning, imitation learning, and deep learning.
Okay, welcome back. Hopefully that gave a good impression of what being at a conference was like. You can see the rest of the video on my YouTube channel, perhaps, if you're interested. But for now, let's go with another example of a paper I worked on slightly later, which was this one. So the problem here was, at a high level, how can we leverage some kind of suboptimal thing you coded up to help a learning agent that is trying to learn things on the same task. So instead of learning from scratch, you can sort of code up some hacky heuristics and try and incorporate them to help out the learning agent without getting into any of the nitty-gritty. And here again, we ended up with a paper, with a talk. I'm gonna maybe slice in a bit of footage of me presenting this at the conference where this was. This was completely different. And yeah.
Okay, hello, I'm Andrei Krenkov, and I'm excited to share with you our work on accelerating reinforcement learning with teachers. Deep reinforcement learning has been promising for complex robotic manipulation tasks, but also hard to put into practice due to it requiring a huge amount of experience. A large part of why there's this need for experience is that agents begin by exploring completely at random, which can be pretty frustrating when you know what the agent should do, such as move towards the door here, which led us to ask, can we use such human intuition to guide agent exploration?
And I don't have any video of the conference itself, but you might find it interesting to see this, which is a little breakdown of all the various papers I found interesting, categorizing them into their respective kind of subtopics. So as you can see, even within a relatively small conference like Coral, which has not a huge number of papers, you can see a lot of different topics and problems and tasks. And yeah, there's thousands of papers every year being published in AI and being presented in different conferences, and a ton of different topics and niches and areas people work in. And so here's a little zoom in of some of the individual topics and different areas where people specialize. Okay, last thing, and then it's done. And then I've gone across what is AI research and what is AI. So let's look at an example that you might have heard of. It's not my research, that is a bit more well known, which is AlphaGo. Here you have an image actually from a trailer that DeepMind made about this project, which you can maybe find yourself. It's a trailer for a documentary. And yeah, AlphaGo, which if you don't know, is a major breakthrough that solved the game of Go, and there was a lot of articles about it, about how it represents a huge step for AI and so on. And it was actually. Go was one of the tasks that was considered very challenging. And so having this result of a system that really beat the best human players, which was not doable until 2016, I mean, it was the first one to do that, was huge. And as you can see here, the way it was done was described in a paper, just like the papers I presented before. And here there were many researchers because it was a large group effort and took a lot of work to get that working. So AlphaGo is one of the major papers of the last decade and is a good example. And it's also a good example of some things to keep in mind with respect to AI research. So one thing to keep in mind about AI research and about how impressive any given new news article is that all research builds on prior work. Okay, very little research comes from nowhere, probably none at all. It all builds on some prior ideas or concepts and expands upon them. And actually, I wrote back in 2016, when I was learning about this topic and was curious about it, a little history of what got us to AlphaGo. And as you can see here, this is the timeline from 1950 to 2016. And there's all these hallmarks along the way of different things that tackle chess, of different results on Go. And AlphaGo is really the culmination of all this work. So whenever you see a new kind of news article discussing a new AI result, one thing to keep in mind is it didn't come out of nowhere. It's not usually some sort of breakthrough, like something completely new. Usually it is building on top of previous things, improving, and maybe getting us across the threshold, as with AlphaGo, where we could actually beat the task in a sense where we could not before. One more thing that I like to note is that AlphaGo is a good example of narrow AI. It's an AI that can only do one thing, and that's again all we have today. Just because AlphaGo can do Go doesn't mean that the same techniques or algorithms can be used to solve something much more challenging, like driving a car or controlling a robot. And in AlphaGo's case, actually you can't. The algorithm, the solution was specific to Go. And that's usually true to some extent for most applications and algorithms and solutions within AI. So let me just quote another thing that combines these points nicely. This is from Andre Karpathy, who was a Stanford PhD and now leads AI at Tesla. And he wrote on AlphaGo back when it released that AlphaGo is made up of a number of relatively standard techniques. However, the way the components are combined is novel and not exactly standard. In all these aspects, DeepMind has executed very well. But AlphaGo does not by itself use any fundamental algorithmic breakthroughs in how we approach RL or reinforcement learning problems. Zooming out, it is also still the case that AlphaGo is a narrow AI system that can play Go, and that's it. Again, this is to some extent usually true of a lot of things that are hyped about in AI. So this is something to really keep in mind whenever you see something that this kind of statement can be made about self-driving, translation, image recognition, face recognition. All these things are usually narrow to that task and usually are building on prior things. There's no immediate breakthrough that is completely new and updrafts the field. There have been some of those breakthroughs, of course, but still those are building on prior work. So there you go. That's AI research. That's what AI is. Those are some caveats to be aware of when you think and see AI and when you are considering kind of AI out there in the real world and are maybe seeing it in media or science fiction. This is what it is in the real world. I hope you enjoyed it. I hope I made things clear. I'm Andrei Karenkov. You can follow me on YouTube or on Twitter, where I sometimes tweet or post similar sentiments about what AI is. And please let me know in the comments what you thought and if any things are unclear, and in general, any of your thoughts about AI. And I hope you have a good rest of this tough year.